Today we're going to cover fatigue fundamentals. We're going to not assume that you know everything, so we're going to go and define all the terms and bring you up to speed so that when you're in meetings where they talk about durability, at least you'll understand all the terms. We're going to start with the basics. Well, why do we do durability? Fatigue is a big part of durability, and the main reason we do this analysis is we don't want to wait till things break. We want to understand if they're going to break before we make them. And obviously, the way to do that is have good models, have good sign-off tests, so validation tests. So I'm a test person and I live in this validation world. So I have two missions as a durability test engineer. I validate designs, and then I validate models. So I take measurements that validate the models, and they do the fatigue in the models because they can quickly make design changes and assess the fatigue life. So as a test person, I'm validating the designs, correlating the models, and hopefully minimizing the amount of development work I do in test, because test development takes a lot of time and money. Here's the whole Simcenter durability process. We're mainly going to focus in this one on the analysis. So analyzing measurements for fatigue content and what goes into that. The testing group is a part of Simcenter. Simcenter is the analysis arms of Siemens Digital Industry Software, and we have CFD, 3D, 1D, and physical test. We're going to focus mainly on the testing side of fatigue, but we do have Simcenter 3D has a durability solver and durability analysis tools in it. Here's what we want to avoid, if at all possible. This is our favorite movie from high school physics. It's the Tacoma Narrows Bridge. Actually, this really isn't a fatigue problem, but it's a cool video. It's a forced response. So the thing that caused that bridge failed wasn't that it wasn't structurally sound, it's that they didn't anticipate the loading as the wind blew through those cables of the suspension bridge. Then it excited a resonance and it just got bigger and bigger and bigger. You can only, any type of material or metal, if you put enough force on it, it eventually breaks. So durability, where did it get started? Where did fatigue get started? It started, well, in 1842, there was a train accident in France. And it was well publicized, lost a lot of lives, and they went to investigate why did it happen. And it turned out that the train was designed with the proper standards at the time, which was 1842, which was for a static load case. They designed these things to carry the load of the train. And what they learned from this was that it's not just the static load that's important, it's also the cyclical load. So as the axle rolls down the track, there's a sinusoidal load on it, and that's what caused the failure. So we're going to assume in this presentation that you get the static load case right, and we're going to focus on loads which vary with time, dynamic loading cases. So you definitely have to do the static, and you also need to look into the dynamic loads, and that's what we're going to talk about. So let's get into some terms. We just touched on it, static strength. It's I'm going to just start loading it, increasing it, pulling it until it comes apart. So it's going to fail in one application of the load. What we're going to spend most of our time talking about is loads which vary with time. So they vary with time and they're below this static strength. Or another way to think of static strength is I fail in one loading cycle. So the big thing is our loads vary with time. Also, we're going to stick, for the most part, to metallic specimens. It gets a little different when we talk about composites. Here's an example of a static strength test on an airplane wing. And I keep thinking that this is going to break any time. It goes quite a while. Hopefully this makes you feel better about flying. Although it seems like whenever the wings touch, they always quarantine the planes. So here, this guy's down here, just broke. So that's a static strength. They just pull it, keep applying a load until it breaks. We're going to talk about loads which vary with time. This is the flutter condition. This is the condition that actually damaged or broke the Tacoma Narrows Bridge. So we're going to talk about loads which vary with time. Hopefully when you're flying in an airplane, you don't see this. They do a lot of work to design against these conditions. Definitions. Durability is the ability of something to perform its function long-lasting and repeatably. Failure is industry specific. So there's two main types. There's crack initiation and crack propagation. So if you can look at the structure, the item, you see a crack, in a lot in the automotive industry, they'll call that a failure. And the reason they call that a failure is they don't know how much longer they have. In certain industries, and maybe in certain types of components, they'll monitor the crack. And when it gets to be a certain size, then they'll have a maintenance schedule. We're going to focus in this presentation mainly on the crack initiation part. So here's some crack growth. They do this a lot in the aircraft industry. So we load it, the crack propagates. So the crack will also propagate from a cyclical load. It'll start to grow, and they want to know that, how it grows. But once they see a crack, they're saying, hey, this thing isn't going to come apart anytime soon, so why should we replace it? We're going to have a maintenance schedule, we're going to monitor this, and we'll replace it at a certain time. That's crack propagation. Here was an example of a bad mistake that happened and caused a catastrophic failure on an aircraft from a crack growth problem. Composites. Composites don't necessarily have a crack in them. They come delaminated. They lose their load carrying capacity. From a test standpoint, we do a lot of the same things. From a simulation standpoint, it's quite a bit different because from metals, we basically have material curves. We use those curves to predict fatigue. In composites, they have to have materials curves, but they also have to model how the fiber is, long fiber, continuous fiber, short fiber. So it's an order of magnitude more complicated. We do have a simulation solution, and if you have any interest in composite simulation, please shoot me an email. I can get you into some of our simulation team that focuses on that. But from our standpoint, we're going to mainly focus on metals from here on out. So what is a crack? Well, it starts, all materials have these microscopic imperfections. And then we take apart and we put it in and we load it and unload it, load it and unload it, and eventually that crack starts to propagate in the metal. When it becomes visible, we say it's cracked, it's failed. And some, depending on how well you can see, is when you detect the crack. But the idea here is that the crack, we don't quite know. Once we can see it, we don't know how long we got until catastrophic failure, which is up here in the upper right. We try to avoid this. The other important part here is durability on metals is all empirical, meaning we cannot model the molecular structure of the metal. We can't model these micro cracks and how they grow. So we use materials tests. So durability, whether you're doing simulation or whether you're doing test, the fatigue analysis is all empirical. It comes from material tests, which we'll talk about. We're not to the state where we can model the full process, which is these molecular structures and micro imperfections. So to finish it off, some definitions. Fatigue is the progressive and localized structural damage that occurs when a material is subject to a cyclical load. So when you hear fatigue, you should think cyclical load. We're going to use stress and strain, stress or strain, are going to be used to calculate fatigue damage. Damage is a measure of fatigue. Some people call it damage, other people call it life. The damage model we're going to use is Miner's rule. We'll go over that. It's a linear damage model. So we're going to use Miner's rule. We're going to add up all the damage. When we get to 1, we say we got a failure. So life is just 1 over damage. So if I took 1 lap around the track and I had 0.5 damage, then I could survive 2 laps around the track. And people in reports and meetings, some people say we'll use life as a metric. Some people will use damage as a metric. I've seen people use hours as a metric. I've seen people use kilometers as a metric, how far you can drive over. So, but typically it's just taking damage and normalizing it, or calculating how many repeats of a loading environment, and then you can get to a total hours. So damage and life, and we'll go over in detail how to calculate damage. Here, just for your records, is the official what is fatigue according to the international standard. Okay, stress. Remember, we're going to use stress and strain. So stress is force over area. Pretty simple. Apply a force, we got an area, we can calculate a stress. There's not a whole lot you can do to reduce stress. You can change the area, or you can change the force. Stress is measured, and it's a unit of pressure. It's a high pressure, so sound pressure is in pascals. Hydraulic pressure is like kilopascals, and stress is like megapascals, just to kind of give you some orders of magnitude of pressure. Typically, I see KSI or MPa. Now, whenever we change the geometry, we need to check the stress. And our CAE friends, colleagues, should be doing this. If we make geometrical changes, we should check stress distributions. Because sometimes people have to do things like packaging. So they have to change the geometry to make this all fit. And whenever you change the geometry, you should take a look at the stress. It has a big effect. Strain's a little bit more complicated, I think, to understand, simply because it doesn't have a unit. It's a relative parameter. It's a change in length over a length. Its units are microstrain because it's really small. So that's 10 to the minus 6. We can relate stress to strain through something called Young's modulus. So here, in the elastic region, we have a slope, and that slope is Young's modulus. It's a modulus of elasticity. There's also shear moduluses and stuff. We're just going to stick with this one. So we have a linear relationship between stress and strain. So all you have to do, when we typically don't measure stress, we measure strain and we convert to stress. And the conversion is easy, but it's screwed up a lot, because this is in terms of microstrain, and this thing is sometimes given in gigapascals. So when you do this calculation, just be careful that you're getting your zeros right. If you're off by a factor of 10, it's really screwy. We see this formula messed up a lot. It's a simple formula, but it's easy to mess up. Just be careful. We'll see a factor of 2 is a really big factor in fatigue. So a factor of 10 is outrageous. So just be careful of that. This equation is only good in this elastic range. As the stress gets more, then this becomes nonlinear. And we'll go into that in some detail. So here, we're doing a static strength test. We're going to just pull this specimen, and if you look at the movie, you'll kind of see where it starts to neck. Okay, so that means it's reducing an area. Now, the point where the force is not going up, the force starts to go down and it's still pulling apart. That's our failure in one cycle. That's called the ultimate strength. Well, in every fatigue analysis, we need the ultimate strength. They don't always ask for the yield point, the yield strength, and we'll see there's several ways to measure that, but that's an example of where we start to go from elastic to plastic relationship. So if it's a linear relationship, stress to strain, we're in the elastic region. If it's a non-linear relationship, then we're in the plastic region. However, it's usually, there's a lot of ways to define this point, and you'll see they can be very different. So we're going to try to give some insight into these points. So here we got some curves. The first we have is the blue and the red. We have the true stress. To get the true stress, we have to count for the reduction in area. And we have the red line, which is the engineering stress. To pick our material curves, we're going to use this engineering stress line. So we talked about the ultimate up here. That's where we're loading it, and the force actually starts to go down, and it's pulling apart. That's where we say we fail at one cycle when we get to that load. Now the yield point's not so straightforward because there's a lot of different definitions. So there's a true elastic limit, proportionality limit, elastic limit, offset yield. Typically, we see this 0.2% offset yield. So what is that? First of all, I was used to strain in a microstrain, but they also do it in percent. So just to kind of give you a little feel of how much microstrain is 0.2%. It's a lot. It's 2,000 microstrain is 0.2%. 1% then is 10,000 microstrain. Okay, so 0.2% offset yield, we go over 2,000 microstrain, we draw a point, line parallel with E, and that becomes our yield point. Now, one thing just to keep in mind, because this is, we want to give you some qualitative understanding, is let's say I say, you know, I don't want to get into a nonlinear stress strain model. One of them's called Ramberg-Osgood we use in fatigue. I'm just going to use Hooke's law. Well, what happens is for a given strain, if you use Hooke's law, you will over predict the stress. Okay, so keep that in mind. If we go elastic and we use Hooke's law, we're going to over predict the stress. So if you make a lot of your decisions on a stress level, then you want to be really careful. Okay, because you're going to this line is just going to keep going up. And this is kind of dramatized. This line I find goes like sometimes up here and then curves, and you can really over predict. So just want to make you aware of that. I hear these terms, but I see this 0.2% offset yield as the common of yield point. That's one measure of where it goes from elastic to plastic. Remember, for in plastic, so if we're elastic, a strain is a deformation in the metal. We deform the metal, we take the load off, and it returns to its original position. That's elastic deformation. Plastic deformation is it never quite returns to its original, and we have some hysteresis. Now, added some terms here just to give you, just for your reference. One I want to focus on is the ultimate strength, just because we have multiple names for it, and depending on the package you're using, you may hear it called ultimate tensile strength, or ultimate strength. It's all referring to that same point. That's where we fail in one cycle. Here's some graphic representations of materials. So the strongest, okay, the highest ultimate, the toughest, the most area, the most ductile, basically like ductile metals would be like, well, silver, jewelry material, gold, silver, stuff like that are very ductile, malleable materials. Give you ideas, some metrics on them, the ultimate strength, these are on elements. Steel is a compound, it has a lot of different elements, it has a recipe for it, but here I'll give you some idea of some values. Fracture-wise, generally we're not here in the ductile, we're more around this region. I don't know of too many parts that are made with ductile materials. Okay, this is our first, I call it the first most confusing metric in fatigue, and it's called the stress ratio. The only reason it's confusing is, notice that, and this is referencing our mean stress. When our mean is really low, far below zero, right, I have a positive number. When my upper mean stress is at zero, I have minus infinity. When it oscillates around zero, which means I have no mean, I'm at -1. When my lower is at zero, I'm zero, so I have a moderate positive mean, and then I have a fraction of a number. So like 0.5, 0.6, when I get I have a large tensile load. Generally, if we're talking tension compression, this is tension, this is compression. If we were talking about shear stress, we have no negative. It doesn't matter which way you load it. It's the same. It's symmetric. So when we get SN curves, we need to understand this R ratio, what it is. It'll be specified. When you see -1, it's called completely reversal loading, zero mean. If you get zero, you have a positive mean. There's another way to look at this. I think it's a little bit easier to understand, and what we're going to do is use the Hague diagram. The Hague diagram is used a lot in durability. It's used a lot in infinite life analysis. And what the Hague diagram is, it'll plot the loading cycles as a function of mean stress on the x-axis and the amplitude of the alternating on the y-axis. So all my tension is over here, and all my compression is over here. And then you can see the R ratio ranges. The Hague diagram, it's used for mean stress corrections, and it's used for infinite life analysis. So that's a lot of our terms and our basics. What influences fatigue? 3 factors influence fatigue: the geometry, the material, and the loading. They all contribute to fatigue. Once we get fatigue, we can add it up and get fatigue life. The geometry and the material, hopefully you control. You write specs, you still have variation, but you have more control. The loads, that's a wild card. If you make parts that run in, say, manufacturing machines that do the exact same thing every day, then you pretty much know your loads. If you make parts, components that go in cars or items that people use, drive or mow their lawn or tractors or truck, then you have a lot more variability. And it's a lot harder to kind of qualify that loading environment. To do a good fatigue analysis, we're going to have to understand all 3 of these areas: geometry, materials, and loads. So this is a very simplified model. We have failure where the loads exceed the structural strength. So we'll just look at our structural strength as a combination of the material and the geometry. There's always going to be some overlap, but we want to manage that overlap. Notice that our loads have more scattering. It's a wider distribution. Typically, there's more variability. There's not generally, in most cases, not a print for the loads, where there is a print and material specifications for the material, and there's also for geometry. So most of our variation comes from our loads. Manufacturing tolerances, well, they should be able to be controlled. They should have your processes in control. So One way is to just over-design. Over-design is we're going to move this structural strength out so there's no overlap. The main industry that I see uses this is oil and gas. So that's I want to drill and I just want to drill. And I'm going to drill as long as I can. And when it breaks, I'm just going to throw it away and put another drill bit down there and drill, drill, drill. Sometimes in the military, but over designing, if you don't go with exotic materials, composites or space age materials, generally it takes mass, weight, thicker materials. And when you add weight in that, you have other attribute trade-offs. So like military applications, they have to be careful. So a tank, if they add weight, they reduce the range, they reduce the speed of the tank. So there's a big trade-off. But oil and gas, it's basically is, keep it going, over design it. They can do that. If you sell to people, customers, consumers, you and me, and we buy things, you can't over design. And that's a big engineering challenging, is managing this overlap. If you've ever done this, well, you just made a mistake. You either totally underestimated your loads or your structural strength. So you messed up one of them. Nobody does this on purpose. This is always a miscalculation at some point. Now these loads, we're going to try to quantify our dynamic loads. So we've talked about the static load. We're going to kind of quantify the dynamic load. So we're going to get stuff like the ultimate strength through the static strength, this pull to failure test. But we're going to have to get our other material properties through dynamic tests. So we're going to cycle these components at various loads and see how long it takes them to fail. We're going to develop these things called SN curves. What an SN curve tells us, it's a material curve. It tells us cycles to failure from a constant amplitude load test. So I'm going to load, I'm going to take a specimen, I'm going to put it in a fixture, in a machine, and I'm going to load it at a certain level until and I'm going to cycle that load until it fails. And then I'm going to go to the next load level. And then I'm going to develop a curve that'll give me cycles to failure at a constant amplitude load. As you probably expect, the higher the load, the lower the cycles to failure. It's common sense. Now, even with a machined smooth specimen that they're going to test, there's going to be variation. Okay. So when I test at load level 1, it's not going to fail at the same time. So generally, and I always get this, I think the minimum samples you would need, what I've been told by some of our fatigue experts, the minimum is 5 loads, 3 samples. But obviously you'd like to have some more if you want to characterize the distribution. You may see this in SN curves because they may say 50%. Typically default is 50 percentile, but they may say 90 or 10 percentile on an SN curve. So there's variation even in machine smooth specimens. And again, these material curves, for stress life, it's an SN curve. For strain life, it's an EN curve. They all do some of the similar tests where they're cycling and fitting. It's just the EN curve has a little more complicated shape because it gets in more into the plasticity. They all have variations. Just to give you a little feel for loading and variation, in typical automotive, loads are 2. You can see the next is welds. Geometry is the best controlled. So materials have lots and they can have different properties. Just remember when you're using the SN curve that you're all using the same percentile. Machines kind of look like this that test the coupons. Okay. So our durability headquarters or our durability development center is in Germany, so we get to learn some German words in there. They're really big. They like to put everything in one word. So the SN curve, it goes through 3 regions. So we're going to cycle at a stress, and we're going to have multiple regions, a high cycle, a low cycle, and an infinite life region. We'll talk a little bit more about these. Notice that, and this is a lot of samples, but it's going to be a fit of these material curves. So the main region is the elastic region, which I would say most parts are designed in the elastic region. A lot of parts are. And this is where we have a linear stress strain relationship. A plastic region, it's where we have a nonlinear. It looks really big, but just remember we're on a log scale. So this is 1 to 10,000. And please take these numbers with a grain of salt. You may stop it at 1,000, 5,000. The other region may go, this one may go out to millions. Usually I see this as a pretty much, it could go a little above a million, but these are qualitative just to give you an idea. So this plastic region looks really big, but it's on a log scale. Nonlinear relationship between stress and strain. And then the infinite life region. This is the region where if we keep the stress below this level, we never accumulate damage. It'll last forever. Just keep in mind on that infinite life theory that if it goes over this level one time, then we calculate damage down here. So it only applies if you never keep it, if you never go above here. And that's why when they do this, they'll talk about design margins, sometimes safety factors, although lawyers don't like safety factors. And that's kind of a factor to say, hey, we know it's here, but we're going to say we can't exceed this just because of variability and safety. So here I'll kind of put it all together on one plot, qualitatively speaking. Now, if you plot it on linear, you get a curved line. If you plot it log, so most all these plots will be on a log scale because we get a straight line. We really want to know the slope of this curve. Speaking of the slope of the curve, this is another one that gets confusing because different vendors and different vendors use different, some use B, some use K, and then certain disciplines define it differently. So I just kind of wanted to do a few slides because I got really confused and I really struggled with this B or K concept. So we're going to go over that to make sure that we're clear when we talk about slopes. So the classic formulation of an SN curve is this formula right here. Okay, so we're going to have a stress level, a number of cycles to failure, an endurance limit, a constant, and the slope of an SN curve. Okay, so a slope of this curve is going to be, they're going to call it's B, and it's a minus 0.33 to general 0.0833. If you flip that over and multiply it by 1, we call it K, and that's a number like 3 to 12. You know, I see 5, 6, 7, 9, stuff like that a lot. So I know 2 packages in their fatigue solver. One asks for K, like our package asks for K, the other people use B. That's the relationship. But then it gets one step more confusing. Then when we do a lot of accelerated tests, Basque-Wynn's law can be, this is Basque-Wynn's law. a variant of Basquin's law. Here's another one. This defines this curve. This guy called Lane arranges it like this. And this formulation is used for something called mission synthesis. It's used to design equivalent damage shaker profiles. And in that case, B is a number between 3 and 12. So in the other formulation, B was a number between minus 0.33, right, and 0.083. So here, B is a formulation between 3 and 12. These are both right. They're not wrong. It's just that you can get wrong answers if you get them confused. Know what you're using. Of the both vendors, I'm saying us as a vendor, we have both vendors have durability vendors that I see a lot have both formulations. So they have this formulation for mission synthesis or accelerated testing, and then one of the vendors uses B and we use K. So just kind of want to clarify that. Technically, the slope is a minus number. It's nice to say the slope of the SN curve. It's just a little bit easier to relate to a number between 3 and 12. And here's a summary slide. So hopefully that helps you. It took me a long time to figure out what was going on with that. It was confusing. Now about this fatigue limit. So certain types of materials have this flat line. Certain types of materials don't. So ferrous and titanium alloys have a distinct limit. So then this infinite life becomes more straightforward. If they don't, then you just have to pick maybe 10 million or somewhere in here amount of cycles and pick a level, and you just want to keep it below that. One reason people do infinite life is that it's hard to count cycles. It's done, I see it done a lot in powertrain testing where something's rotating and there's getting loads every time it's rotating. If for some reason you cannot find the materials or you don't have the material databases, you can calculate materials from the uniform material law or the universal slope law. And all you need is the ultimate and Young's modulus. And you can derive, and there's like PhD theses done on that. It seems to be okay for, on-off highway type materials. Aerospace, I don't see them ever using something like this. But the thing I like about it is this whole fatigue it's relative. It's very hard to predict exactly when something's going to fail. So to say, if you say something's going to fail in 1,000 hours, a good prediction of fatigue would be if you went 500 to 2,000. So a factor of 2 is good for actual life to failure on a real type of part. A bad is a factor of 10. So if you don't have a place to start and you don't have a material property, it gives you it gives you a starting point. And you can always take materials that you have, plug this in and calculate it and see how close they are. So here's some examples: steel, iron, aluminum alloys, copper. I want you to keep, I like rules of thumb, things to just keep in your mind. The ultimate to the endurance limit is a factor of 2 on steel. Okay, so 690 is our endurance or fatigue limit, so that would put it at 1380, typical steel. These are just qualitative rules. The reason this is important is some people, when they want to accelerate a test, they'll increase the amplitude. So if your loading environment's starting up here and you increase by 2, you're it's not going to end well. It's not going to be a good test. So when you increase the amplitude, you want to look at 10%, 15%. Again, here's the aluminum curve. So if you're doing infinite life, they just got to pick a value out here. So how do we get to damage? Well, we'll start with some waveforms that we're very clear on. We'll take a sine wave. So a cycle is basically a period. Here we have 2 cycles. We're going to cycle it at a certain amplitude, and then we're going to go over there and to the SN curve, and we're going to say, hey, how many cycles will it last? Remember, an SN curve is cycles to failure from a constant amplitude load. In this case, it's 6. So my damage is just 2 divided by 6. Then I take a bigger waveform, another waveform, and I got 2 cycles of that, but it's bigger, so it's not going to last as long. So that's 2 divided by 4, and that's 0.5. I add that together. Linear damage model, we just add it together. So and then I add it up. It's less than 1, so I haven't failed. If I added another cycle, another high cycle, add it up, we're over 1, we have failure. That's all there is to the damage model. There's other damage models. Some people have fancy damage models, nonlinear damage models, whatever you want. Typically in commercial code, you're going to see Miner's rule. It's a linear damage model. Couple of things to keep in mind. It's rate independent. So it doesn't matter how fast you cycle the sine wave. We know that's not true because we generate heat. So it's rate independent. The theory of fatigue is rate independent. If you're doing a test and you're doing one of these rigs and you're exciting it, generally ballpark rule of thumb's 10 degrees. You don't want to raise anything more than 10 degrees. So it's rate independent. We just count cycles. It's easy to count cycles on a sine wave. If you like a more mathematical formulation, here's one. Here's another expression for damage. Adds them all up. It's also not just Miner's rule. It's really Palmgren Miner's rule, but it seems we all shorten it to Miner's rule. Here's a little table that lets you know about this raising the amplitude, reducing the cyclic loading applied to an optimally shaped steel component with 13% doubles the life. So here's my load. Here's my slope of my SN curve. This will change as a slope, but if I increase 15, I go down. You can see small change in load, big change in life. If you want to see it as a function of the slope of the SN curve, the higher it gets, or the K, the higher it gets, the more effect it has. Now, very few people put these machined, smooth specimens in their products. So there's going to be some adjustments to the SN curve. So adjustments for size, surface finish, mean stress, loading type. We handle mean stress in a different way. Okay. You can either handle it by changing the SN curve, or you can handle it by changing the cycle. We move the cycle, but either way is good. They both have the same result. So typically, these will have an effect. So think about a rough surface. A rough surface has more of a propensity to have some kind of imperfection that when the load cycled will crack. So if it's really rough, it'll form a crack before a machined smooth surface was. Size is a little bit confusing. That for the same stress, size has more surface area, more opportunity for imperfection. And I didn't put all the slides in here because there's research to support this. So, and I do have a durability presentation if you're interested that goes in a little more detail on the effects, and you can look them up in tables and they'll give you like how much to adjust this curve. There's a couple of different ways to adjust it. One adjusts this just to one slope, and the other adjusts here at the 1,000 mark. What we're going to adjust by, don't get confused by the terms of stress concentration factor. What we're really interested in is something called a fatigue notch factor. There's a bibliography in here because a lot of this stuff is taken from, like this slide's taken from a textbook. There's a good durability textbook for simulation and test fatigue. If you're interested, I can send you the bibliography or the reference to it. So we're not, you can see the derivation from stress concentration, but we're talking about fatigue notch factors. It's going to tell us how much we lower our SN curve. There are some ways to increase, and those have to do, but they're not covered, have to do with like surface treatment and certain types of surface treatments. Generally, rule of thumb in tension compression, tension decreases life. So if I pull something apart and I oscillate it, it has lower life than if I compress it. Compress it helps us for fatigue. Our problem with fatigue is that we very rarely have a sinusoidal loading. So we have to figure out a way to go from a complex waveform to these cycles. And what we're going to use is something called rainflow counting. So rainflow counting extracts the damaging events from time series, and it uses a rainflow matrix as an accounting tool. So the basic damaging event is a closed hysteresis loop on a stress strain curve, and rainflow counting extracts those. Once I extract all these cycles, and what do I need to know about the cycle for fatigue? I need to know the amplitude and the mean and the number of cycles. Once I have that and an SN curve, I can calculate damage. So rainflow counting is the tool we use. Now, in the rainflow matrix, there's some lines. Again, this is a way to keep track of all the cycles in our waveform. If you go from upper left to lower right, this matrix is also called, a from to matrix. That says a cycle goes from this level to this level. So upper left to lower right has 0 damage because this is a cycle that goes, say, from 10 to 10, has no range. If it has no range, it has no damage. The cycles that are way out here have high damage. This kind of perpendicular line through this cross here is a 0 mean line. So that's R equals -1. There's some more caveats. You can also see compression and tension, hanging and standing. Hanging and standing has no impact on damage. So this cycle over here has none. So a lot of times they fold it over. They only look at one side of these, but it's needed to keep track of for reconstruction algorithms. So 0 mean, compression, tension, cycles out here have a lot of damage. Now there's different ways, different vendors look at this. In our software, we can do all of them, but we have the unsymmetric, which I like because it gives the prettiest designs. We have a symmetric, which is just we fold it over hanging and standing. And then if we rotate that, we can get range mean. Now it's a big problem to, how do you overlay a 3-dimensional plot? You don't. So we need to get it to 2 dimensions. So then we can either correct for the mean or remove the mean and just look at the range. And this is called a range pair diagram. So this tells me how many cycles I have at a given amplitude. Generally, I'll have a lot of low-level cycles and smaller high-level cycles, but based on our SN curve, these are what's really damaging. Then I can integrate that and I can get a cumulative cycle count, range pair. So what this tells me is how many cycles I have that are above this value. So if I go to my 100 cycle count and it says I have there's 100 cycles that are above this value. And then there's 100, this is the total number of cycles that's above 0. Or above the middle of the bottom bin. Once I have this, then I can get a cumulative damage. So what this tells me now is I know, so you can also look at this instead of damage as a percent. So if this was I'd normalize this, and that would mean that at 40%, I have almost above 40, the cycles above 40 contain almost 100% of my damage. This is a very important plot because it says that cycles that are below 40, or maybe you want to be a little more conservative and go 50, cycles that are above 50 create 97 or 8% of my damage. When this line goes vertical, it means that they're not really that important in fatigue. So when we do accelerated testing, part of the magic is how do I get rid of those cycles? And here is a component SN curve. So because sometimes what happens is people want to get an idea of what the component's doing versus the materials, so they'll run cycles. I've seen it done on exhaust hangers where they'll pick 3 or 4 amplitudes and say cycle some parts to failure just to get an idea of how they're behaving. If you use a component SN curve, you don't need to use the correction factors. The problem is they're cost money to get. Okay. So what I'm going to do is jump into the software and just show you some examples, and then we'll be done. So just some basic analysis. So there's 2 types of analysis we do, a relative analysis and a more formal analysis. So the relative analysis, all I'm going to do, and test guys do this all the time, I'm going to take a waveform and I'm going to rainflow count it, and I'm going to apply some generic SN curve. And I don't care whether it's stress, strain, acceleration, displacement, I'm just going to get an idea of the damage. Sometimes we call that pseudo damage or quasi damage or relative damage. So I'm going to dump this in the input basket, this data. So it's a 3-dimensional load cell. Now this is in force. An SN curve has to be an MPa or pressure. If I want to do an analysis, I would have to relate this force to get it to the unit. But I'm not so concerned about that. I'm just concerned about understanding which directions I should worry about, which directions have all the damage in them. If you need a down and dirty rule, it's usually the range. If you don't do mean stress, if you look at which has the most range, a lot of times has the most damage. Not all the time, but a lot. So here what I'm going to do is I'm going to take the input. I'm going to calculate a rainflow matrix. I tell it the number of bins and a hysteresis filter. So my filter width is 1 bin. Then the superposition, what it does is usually I don't measure 1,000 laps around the track. I maybe measure 1. So what this allows me to do is scale it. It also, if I want to do this over multiple tracks, I can say, hey, track 1 is 1,000 repeats, track 2 is 2,000, and then I can get my assessment. So I could take into account multiple tracks. That's what the superposition. Then I calculate the range pairs, then I calculate the damage. When I do a damage, a lot of times I just use a generic SN curve, but if you really did get it to stress, you could select the actual SN curve. Remember, I can do this with anything. Acceleration, I'm just trying to quickly compare. Is track A more than track B? Design A more than design B? Driver A more than driver B? Now I can run that, go to my output, and then I can look at my plot. So here's my rainflow matrices. It's pretty hard to tell anything from rainflow matrices, although here it gets a pretty design. You can see this one is right in looks like it's the vertical, so it looks like it has It's all down here, so I believe that's in intention. This has a big positive. This goes across, so this has positive and negative load. Remember, this diagonal is zero mean. Quickly, if you just look at your range, 1190 to minus 715 versus minus 6 or minus 6 to 10,000. You can tell from that what's going to be the most damaging. And here goes from minus 4,000 to 11,000 or so. Still, nice pictures, but hard to overlay. So now we can look at a range pair. Range pair is going to give us the number of cycles, but the one we look at a lot is range pair damage. This is in damage values. So you can see from here, the lateral is the most damaging, the vertical, and then this one is significant orders of magnitude. Let's see. I can also get this to percent. So you could look at it in the basis of percent. Format normalized. So now this is a lot easier way to look at it. The red one's 100%. The vertical was 37%, and the longitudinal is almost nothing. So if I'm designing a test, I'm going to take into account these two. Now I did nothing to correct for mean stress, which I could have. So this is a powerful tool. It's very quick. It's the basis for a lot of accelerated testing. It gives you a good idea on a relative basis. Then the last thing I'm going to show here, we're going to do a fatigue analysis. So we're going to do a basic stress life analysis. I'm going to take a rosette here and I'm going to plop it in. Now we're not going to do the fancy rosette math, multiplane. We're just going to calculate each one of these rosettes. This will show you why you need to use a rosette. It gives you strain in a plane. So these are a 0, 45, and 90 rosette. I'm going to do my rainflow counting. Now I'm going to go into a stress life analysis. So now I'm telling it what Young's modulus is, so it'll automatically multiply for me. And I'm using the fatigue properties of Miner's elementary rule. I'm ignoring mean stress, and I'm using the endurance limit. So that means if I did not have a cycle that went above the endurance limit, I wouldn't get any damage. But once I go above it, based on this rule, I will count damp cycles below. So I've got that rosette, and I'm going to run it. And then I'm going to go over here, look at my results. And again, you can see my rainflow matrices. Let me just look at one of these. So here basically I have the histogram of my loads. This is my SN curve, and this is my variable amplitude SN curve. This is basically a life curve, a Gaussner curve. It's built from this curve here. So this is from a constant amplitude load test. This curve is from the variable amplitude. And why this curve is pretty cool is that if I scale this load, I slide up and down this design point. So this is design point. If I go down here, it tells me how many times I can repeat this loading environment. So this is the basics. What people look at, they don't look at all that. They just go over here and they click on this statistics and they look at this. So I chose to solve it in blocks, repeats. I can repeat that curve, that loading environment, 1,086 times before I get to 1. If I click on all these, now it says that my 0. But here's why I always caution you about using one strain gauge. If I would have just put one strain gauge and I'd have put it at 90, look at the difference. So obviously the lower the number, the more damaging the direction of the gauge is. So a gauge, if you rotate it, can get significantly different max damages. So typically we resolve this every 10 degrees, calculate the damage, and take the max one. It's called multi-axial fatigue. But this is a very quick hitter. I just want to see which one has the most. And I can do this in life as well, and I could also do it in hours or something like that if I wanted to.
John,
But that's basically it. Thank you for attending.